Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been discussing about transition metal carbonyl halides in the last lecture, and there we have looked into various preparative methods for transition metal carbonyl halides, and in this lecture we are going to look at some of the applications of these kind of complexes transition metal carbonyl halides, and then look into another very interesting class of compounds. These are transition metal alkene complexes. As we sort of look at the compounds that we have discussed so far, what it seems that these are extremely important compounds, particularly from the catalytic point of view, in the sense that they are active catalysts for many important and useful transformations which are being routinely used in industry as well as in academia alike. So, that is what is the hallmark of organometallic chemistry, and that we have started appreciating as we have looked at some of these transition metal carbene, transition metal alkyne, transition metal carbonyl complexes, transition metal carbonyl hydrides, transition metal halides that we have been discussing. Apart from that, what strikes out is the fact that apart from chemical catalysis which organometallic compounds are usually known for, they can also be used as good reagents for carrying out various organic transformations, and one very good example that we had discussed about the reagent applications of transition metal organometallic compound is the Coleman reagent, which is the iron based metallate, disodium iron tetracarbonyl metallate, which is extensively used for functionalization of organic halide compounds to various functionalized organic compounds. And we saw that the hallmark of Coleman's reagent is that it produces these functionalized compounds from organic halogen compounds in very good yield, high yield and high selectivity. We have discussed extensively on that in the previous lecture. We have also looked into another important organometallic compound which serves as a reagent for various important organic transformation, and this had been the Tebbe's reagent, which was a titanium carbene complex which we had discussed in our earlier lectures. So, what we see that from the applications of transition metal organometallic compounds, there are two phases to it. One is obviously the catalytic applications, which is predominantly occupying the greater space in application space, and the next big thing about organometallic chemistry is these applications as stoichiometric reagents, for which we have just looked at Coleman's reagent as well as Tebbe's reagent, and we see that these are no less important, and they are equally useful and are being extensively used for their utility purpose. So, with that we are going to discuss some more applications of transition metal carbonyl halides in this current lecture. And one important thing about these carbonyl metal halides, that they can be used as precursors for preparing metal-metal bonds. Are often used as precursors for the formation of metal bonds. A good example of this is given in the reaction below. Mn CO5 bromide reacting with rhenium CO5 metallate anion gives CO5 Mn rhenium CO5 plus Br minus. So, this is a interesting reaction where or interesting application of carbonyl metal halides, where this is nicely used for preparing this metal metal bond. And another interesting bit over here, that this is a heterodinuclear compound in the sense that there are two different metals in this dinuclear compound, and that is synthetically very challenging compound to make as far as the synthesis is concerned. And these are very important compound particularly in chemical catalysis perspective, because these two metals will have different affinity or will exhibit different affinity for different kind of substrates, and as a result it can activate more variety of substrate simultaneously, giving catalytic products which otherwise are difficult to obtain using the homodinuclear counterparts or homometallic complexes. So, from that perspective, this method is a very nice application of transition metal halide complexes to produce this heterodinuclear bimetallic species containing metal metal bond. And obviously, understanding the molecular orbital picture of this metal metal bond itself is a very interesting problem by itself, and that also is extensively being studied as to how or what kind of orbitals are involved in formation of this metal metal bond. So, with that we conclude our discussion on transition metal carbonyl halide complexes and move on to another very interesting set of ligands which are sigma pi donor pi acceptor ligands. Now, these are interesting class of ligands, first of all, that make bonds to transition metal. By interesting, I mean these are electron rich species which has filled orbitals like the homos or the homo minus 1, which can interact both in a sigma and pi fashion with the metal with appropriate orbital symmetry, and also it has empty or vacant LUMO or pi star orbitals which can accept electron density from the metal, and hence is the π-acceptor nature of these ligands. So, one good thing about this ligand that they can give electrons, to metal, which is very common for any ligand, that they give electron to the metal, and this giving of electron can occur from by a sigma or pi fashion. But the other interesting aspect of these ligands are they can accept electrons from metal. Now, this is counterintuitive concept for a ligand, because ligands are known to be electron rich species which donates electron to a electron deficient metal. So, how can electron rich species accept electron from electron deficient entity like metal? So, in that way this π-acceptor concept is sort of a concept which is counterintuitive to the normal definition of ligand, and that is why this kind of sigma pi donor π-acceptor ligand are so special. So, these the examples of these ligands include compounds like olefins or alkenes, even alkynes. So, these entities make bonds with transition metal can bond in similar fashions, where they can donate electron through sigma and pi donation and also accept electron as a pi acceptor ligand. The other examples of these ligands are C3R3 A plus or C4H4 or C5H5 ligands. So, cyclopentadienyl, cyclobutadienyl or cyclopropenyl frameworks or belongs also to this category of ligands. So, with that said, we are going to focus begin our discussion on this sigma pi donor pi acceptor ligands right from its first example, which are the olefins. Now, transition metal olefin complexes are important complexes, and they are catalytic intermediates in hydrogenations, oligomerizations, polymerizations, so on and so forth. Important catalytic intermediates. In hydrogenation, this is a very important reactions where olefins are converted to alkanes. Oligomerizations, or polymerizations reactions, cyclization reactions, hydroformylation reactions, isomerization reactions, and oxidation reactions. So, what we see that these are extremely important species or compounds or class of compounds which can carry out whole gamut of very important reactions. And as to highlight that many of these reactions have been recognized for their utility by the conferment of Nobel Prize. So, for example, hydrogenation has been given the Nobel Prize, polymerization, this ring opening metathesis reactions, cyclizations, hydroformylation. So, at least what we see that 4 of these so 8 or 9 applications that we have been discussing, 4 or 5 of them have been recognized by for their utility by conferment of Nobel Prizes. So, these are extremely important compounds, and these transition metal olefin complexes, and that can be seen from the kind of utility that transition metal olefin complexes exhibits. So, with that, let us discuss in bit more details about these transition metal olefin complexes, particularly about their stability, their preparative methods, and also their reactivity, along with some of the applications of these transition metal olefin complexes that we are going to be discussing. So, preparations, usually the first this transition metal olefin complexes was prepared long back. The first one was Zeise's salt. The first method was discovered way back in 1827, like that is about like 150 years or more earlier, by Zeiss, and the reaction was done by taking K2 PtCl4 plus C2H4 with dilute HCl and 60 bar pressure gives K C2H4 PtCl3 KCl. So, this was prepared by boiling PtCl4 in K2PtCl4 in ethanol. And one interesting thing is that this reaction was improved on several counts, and one interesting thing to note about that this compound, even though discovered in 1827, its understanding of this compound as to how it binds, as to what are the bonding interaction that this ethylene displays with the metal, that only came to be known about more than 100 years later of its discovery in 1950s and 1960s, when the Dewar-Chart-Duncanson model was proposed to explain the bonding of transition metal olefin complexes. So, here is an interesting example which was understood really about 130 or 140 years after its synthesis, and then like the various other applications of these complexes or this class of complexes emerged. So, what is interesting to point out with regards to Zeise's salt, that here is a compound which has never lost its sheen right from its discovery so long back, and then it could engage the community for such a long time and provide an interesting bonding theory that solely developed on this complex. So, in that way this is a very landmark interesting compound, which was not only interesting from its synthesis point of view, but also was equally interesting from the theory it developed for the understanding of the binding of the olefin to the metal center, which was done in 1950s, about 130 years after. So, there are other methods also available for preparing these transition metal olefin complexes. The one involves using AlCl3. AlCl3 is a Lewis acid, and that abstracts Cl minus to form AlCl4 minus and the corresponding metal olefin complex, and this is nicely demonstrated in this reaction of ReCO5Cl plus C2H4 giving AlCl3 and ReCO5 C2H4 AlCl4 minus. So, what happened over here, this chloride got abstracted by AlCl3 to give AlCl4 minus, and the vacant space produced over here got occupied by this olefin or ethylene C2H4. The way AlCl3 was successfully used in forming this rhenium olefinic complex, similarly AgBF4 can also be effectively used for making the metal olefin complex. Leads to precipitation of Ag halide and the complex. So, these can be seen nicely in this iron example, where Fe iodine plus C2H4 in presence of AgBF4 gives Fe CH2 BF4 minus plus AgI, which is precipitated out. The counter anion and the abstractions of this iodide by silver giving AgCl produces a iron cationic iron species containing this coordinated olefinic compound, and then the anionic charge balance is done by the BF4 moiety leading to this formation of this ionic compound. Now, apart from this abstraction reactions with Lewis acids or silver salts, thermal ligand substitution is equally effective for producing these transition metal olefin complexes, and an example of this is shown here. So, FeCO5 plus this diolefin at 135 degree centigrade and 20 bar of pressure gives this diolefin iron plus CO. So, here what we saw that this carbonyl got replaced by this olefin leading to these olefinic compounds. Now, usually it is known that carbonyl binds very tightly to the olefin, and that has been achieved, the dissociation of the carbonyl from the iron has been achieved by heating under forcing conditions. Forcing conditions, I mean the temperature is about 135 degree centigrade. So, through heat or through thermal conditions that these carbonyls are made to dissociate, otherwise carbonyls bind very strongly to iron, and also the olefinic condition is 20 bar, it is like extremely high pressure of olefin, then only you can replace or one can replace carbonyl with olefin, because olefin does not bind as strongly as that of a carbonyl. So, under very forcing conditions of about 135 degrees centigrades of heating and 20 bars of olefinic pressure, that one can replace this 2 carbonyl moieties by this diolefin to give this butadiene FeCO3 moiety. The way carbonyls can be substituted by heat, the same can be achieved by photochemical reactions, and the example of this is given below. The example is Cp Mn CO3 plus this olefin in presence of light is MnCO, and one of the carbonyl is replaced by an aldehyde. So, here also we see that this dissociation of the carbonyl is achieved by light, and in this case this has been achieved by heat. And one must sort of take a note of this fact that this is a 18V complex. So, for this addition to happen, it has to undergo a dissociative mechanism before the olefin can bind, and for that the dissociation of the carbon monoxide is very crucial, and that is achieved under forcing conditions, because carbon monoxide being a pi-acidic ligand bind very strongly to the metal, and that it requires forcing condition to be replaced by some weak ligands like olefin. Similarly, the case over here also this complex is also a 18 electron complex, and for it to react with this olefin is difficult. So, it also goes by a dissociative pathway, and this dissociation is achieved in presence of light photochemically, where one of the CO is dissociated, it goes to the 16 electron, and when the olefin comes and bind. So, another two methods which are there for producing this transition metal carbonyl olefinic complexes. One is such method is called metal-induced ligand isomerization. An example of this is FeCO5 plus this OMe. When this is heated at 140 degree centigrade, this diolefinic compounds isomerizes and become conjugated to give the more stable one, and that binds to FeCO3 plus 2CO. So, here also we see that metal induced ligand isomerization, this ligand is isomerizing, and the loss of CO has been achieved under very high thermal conditions of 140 degree centigrade. Sometimes separations of isomeric olefins by recrystallization with AgNO3 adduct also gives the metal olefin complex. Example of this is given AgNO3 plus olefin in ethanol gives the silver olefinic complex and NO3 as the outer sphere. So, this is a very useful and convenient method for making this olefinic complex with lead transition metal by recrystallizing silver nitrate and olefin from ethanol, leading to this silver bisolefin nitrate complex. So, with that, let me conclude the discussion that we have had in today's lecture. We have looked into started this lecture by looking into one of the utility of transition metal carbonyl halide complexes, and what we see that these have been extensively used for preparing dinuclear heterodiatomic transition metal complexes, which are very challenging compounds to make, and this transition metal carbonyl halide provides an effective route for producing these heterodinuclear complexes by reaction with transition metal carbonyl metallate anions. So, we have looked into that utility aspect of this transition metal carbonyl halide. Apart from that, we have also looked into this new class of sigma pi donor pi acceptor kind of ligands, these ligands include alkene, alkyne, as well as these cyclic olefins like cyclopropane, cyclobutane, cyclopentane rings, and we have looked into the various preparative methods available for preparation of these transition metal olefin complexes. We have looked into some of the examples. One thing I must note in the perspective, this perspective of transition metal olefin complexes, that they are important intermediates, and in various catalytic reactions, about 8 or 9 of them, and 5 or 6 of them have been recognized for their utility with Nobel Prize. So, that sort of speaks volumes about how important these class of transition metal olefin complexes are. So, with that, I would like to conclude today's lecture, and we are going to be discussing more on this important class of compounds, this transition metal olefin complex, in the subsequent lecture. Till that time, goodbye, and look forward to being with you in the next lecture. Thank you.